What's that? Questions about anything? Anything going right? Yes. Oh, this is the one we. Let's see if I have that extra one here. We've been working on this one for a couple of days. Let's see. All right. There you go. This is on the board. All right. Well, last time we talked about creating matrices for any transformation with respect to bases of the codomain or the domain and the codomain space. So remember, the process is we plug the basis vectors into the transformation and figure out what their coordinates are, the output coordinates are, with respect to the basis for the codomain. And we put those in as columns. And then those give us the coordinates that we need to use for the outputs for any vector that we have. So let's do this example. This one we actually have a linear operator. It happens to be the derivative operator. So plug in a function, take its derivative. That's what we mean by the derivative operator. Okay. Again, using the word operator, all we mean is that it's a transformation from a space to itself. That's the only thing that difference is what we use a different name. Anyway, they tell us that we're going to look at a particular subspace of differentiable functions. In particular, this subspace is generated by e to the 2x, x e to the 2x, and x squared e to the 2x. So just a three-dimensional space here. Okay, it's generated by those three vectors. We can check that they're linearly independent quickly, but they are linearly independent. So the three-dimensional space. So we'll have a 3 by 3 matrix when we're done. This is we're going from the space to itself. We'll plug each of those, again, we're going to plug each of those vectors, in this case functions, into the transformation and figure out the coordinates with respect to the same basis. That's why we just used a t sub b there. It's going to be the same basis for input and output space, so we just use a single letter for that. Okay. All right. So we differentiate each of these. Derivative of e to the 2x is going to be 2e to the 2x, good. For x e to the 2x, we'll have to use the product rule. We'll get an e to the 2x and then 2x e to the 2x. You're exactly right. I'm going to leave it like that, though, so we can get the coordinates easily. You're exactly right, though. It is x plus 2, or it is 2x plus 1. But I want to leave it like that so we can get the coordinates with respect to the basis vector. For the other one, what do we get? Good. Good. Yeah, exactly right. All right, so those are the derivatives that we have for our three basis vectors. Now, again, the next step is that we want coordinates of these with respect to the basis of your output space. Oops. I could write the right things. Again, the input space, output space, we're using the same basis for both. I'm just writing sub b here. But again, the next step in your process is to find the coordinates of each of the outputs with respect to your basis for the output space, for the codomain. Again, our basis is e to the 2x, x e to the 2x, and x squared e to the 2x. In that order, what coordinates would you have for that first vector? Good, 2, 0, 0, fantastic. For the second one, 1, 2, 0, and that was why I didn't factor it, so I could see what the coordinates were easily. And then the last one, 022. Good. Fantastic. Good. So then again, our matrix will be, we take those coordinate vectors and write them as columns. So we'll have 2, 0, 0 down the first column, 1, 2, 0 down the second column, 0, 2, 2 down the third column. Notice again, one of the reasons why we like, we're going to answer the final question here, but one of the reasons why we like matrices to represent our transformations is because we can row reduce this and check if it's one-to-one onto and or onto, right? In this case, this is upper triangular, and every element on every entry on the main diagonal is non-zero, so it's definitely going to be invertible. So I'll get a pivot in every column and every row, so it is one-to-one and onto. Right? Check that easily. I don't have to do anything here. I can look at it and tell it's going to be one-to-one and onto. Okay. Now, when it asks us to compute the transformation, we can do that again by using the matrix we just found and doing matrix multiplication. So we're actually going to calculate the coordinates of the output and then use the coordinates to tell us what the answer is. That's why I wrote it this way. So again, the whole point of doing this is so that we can calculate outputs of the transformation through matrix multiplication. So this is our transformation matrix in terms of input space and output space bases. I need my input here to put into the transformation, or I need my input to get multiplied by the matrix. This input vector needs to be in terms of the basis for the domain. In this case, it's both, right? But I need this to be the basis for my domain. So my input here is 4 e to the 2x, 6x e to the 2x, and minus 10x squared e to the 2x. What coordinates are we going to use here for that vector we're going to multiply by? Yeah. Again, same idea, right? Then we multiply, we'll get 8 plus 6 is 14. 12 minus 20 is negative 8. And 2 times negative 10 is negative 20. So what function comes out? What is the derivative of this, reading it off of there? Good. Yeah, those are the coordinates for the output, right? That's the whole idea here, right? We use the coordinate vector for the input, use this matrix that basically is just telling you how it transforms these vectors in the input space to the vectors in the output space. That gives me coordinates of the vector in the output space, so I use those coordinates to write down the answer. So we just differentiated this function without doing any derivatives. We did matrix multiplication to take a derivative. That was kind of fun. I thought it was kind of fun. And you can check that this is the right answer. This gives me 8e to the 2x. When I differentiate this x here, I'll get a 6e to the 2x. 8 plus 6 gives me the 14e to the 2x is what I'll be done with what I'll get when I collect those terms. I get a 12x and then a minus 20x when I differentiate this x squared on that one. 12 minus 20 gives me negative 8. And then finally, if I differentiate this one, I'll get a negative 20x squared. So we really do get what we said we get. This to me is kind of fun because, again, we're doing differentiation without actually taking a derivative. Which, by the way, if you give a set of basic rules to a computer, this is how it's going to do it. It's going to figure it out according to these rules, these matrix ideas. It's going to know how to differentiate basic functions and then use those ideas to get the new ones. This is exactly what we did, right? Derivatives of some basic functions and then use those rules to give me the derivatives of things in terms of those basic ones. All right, so this one's a little bit different. It already gives you the matrix of the transformation in terms of two bases, which I've written down there. The first thing it asks should be a relatively easy question. It asks you to figure out what the coordinates with respect to B prime are for each of the vectors in your basis for your domain. So again, when we write it this way, the B is the basis for your domain, the B prime is the basis for your codomain, right? So remember, how do we fill out this matrix? What do you do to fill out this matrix? What did we just say we did? So you put the basis vectors into the transformation, right? Do the transformation and then find the coordinates with respect to the output basis, right? And then you put those in as the columns, right? So just looking at what it's asking you to do, if I apply the transformation to 0, 1, 1, 1 and calculate the coordinates with respect to B prime, what does it have to be looking at the matrix? Yeah, it has to be the 3, 1, 3, right? Remember we put them down as columns, don't we? When we apply the transformation to the first vector and find the coordinates with respect to the output basis, the codomain basis, we put it in as the vector here, right? In that first column. Second one then has to be what? Yeah, -260. Yep, exactly. For the third one, well, the 127, good. And then the last one has to be the last column. Basically, it's deconstructing, right? It's basically deconstructing, right? We know what the matrix was, or is. How did we create it? To create that matrix, we had to put each of the basis vectors in and find the coordinates of those outputs with respect to the output basis and fill in the columns. So those columns have to be the answers. So far, so good? All right. Now, instead of asking for the coordinates, it's asking you for what the actual outputs are. So it's asking you what vector actually corresponds to t of 0, 1, 1, 1. How do we use this output? What do we do? What are those? It's not the output vector directly, it's the what of the output vector? Coordinates, right? It's the coordinates of the output vector, right? That says take 3 times your first basis element plus 1 times your second basis element times -3 times your third basis element. That's what that says for that first one, right? So this output will be 3 times 0.88 plus negative 781, and then minus 3 times negative 691. Whatever that turns out to be, right? And then to figure out the transformation in terms of, for each one, you just plug each of those in, right? So you would need to do, so your transformation of 2, 1, negative 1, 1 would then be what? You use negative 2 times 0.88, 6 times negative 781, lost track of where I was, and then 0 times negative 691. And do the exact same thing for the other two. Does that make sense? What we're doing there? So I'm not going to go through the last parts because I want to get to some new stuff today, and that's going to take me longer than I wanted to spend. But once you get these output vectors here, if you want to find a rule, we talked a little bit about this before. If you want to find a rule for the general W, X, Y, Z idea, remember that we can, this is when we use GeoGebra to help us out a little bit. Remember, we could take each of these input vectors or not input vectors, each of those basis vectors, and find the coordinates of the input with respect to that basis, right? I could do it by hand, but I really don't want to. And I don't want to take the time to put it in GeoGebra. But you would get the coordinates of your input for an arbitrary W, X, Y, Z in terms of each of these. Then you would know what the outputs are based on what you get here, right? Because this gives you the outputs, the actual vector outputs for each of these particular inputs, right? So then I can write the output for W, X, Y, Z by using our properties of our transformation by writing it as a linear combination and then splitting it up, right? So again, if you're, I'm not gonna, like I said, I'm not going to go through the whole thing because I don't feel like doing all the computations. But say your W, X, Y, Z is A times the first vector plus B times the second vector, C times the third vector, and D times the fourth vector. That way, yep, that's what I wanted. If I have those, these A's, B, C, the A, B, C, and D here would be in terms of the W, X, Y, Z, whatever it turns out to be. Then when I do the transformation of that, I can pull out the constant of each of those and break it up over the sum that way, right? We agree? We can do it that way. That's the whole point of having. That's the main characteristic of being a linear transformation is literally to be able to do that, right? If I have those four outputs, now I can get the outputs here in terms of for my V1, my V2, my V3, my V4 by doing this part, and then simplify, and that'll give you your rule. It'll be in terms of W, X, Y, and Z. And then once you have the rule, then you just need to plug in 2 for W, 2 for X, 0 for Y, 0 for Z. The answer to the last part. The whole point of this particular exercise was that if you know what and this is just another way to say the same thing we said before, if I know what the matrix is for the transformation, then I know what the transformation does to the basis vector, so then I know what the transformation does to every vector. And we talked about that before, right? If we know what the transformation does to a basis, we know what the transformation does to period. This is just another example of that, just from having the matrix to start with. Does that make sense? Okay. Lots of computations. They basically illustrate that point again. So that's why I didn't want to go through all those computations. Main thing is, do you have any questions about how we created these matrices? Okay. All right. Well, let's go on and then talk about one last thing, and that's about finding inverses of linear transformations when we can.
Was it Sundays? The website.
Or there was some of the inverse already on there? The one you already had to do?
No, it's 2 Sundays.
Oh, do Sunday.
Oh, it's next Sunday?
And I know.
3 is
Yeah. I'm gonna move it to May 2nd. All right.
Take one.
Oh, you take it.
Yeah.
Oh, you're just taking it. Okay. You don't need one.
Nope.
I emailed that to you this morning.
Oh, okay.
Yeah.
Sorry.
No, that's okay. If you want now. No. Oh, okay. I'm sorry. If you need it, I can give it to you. Okay. Well, then fine. I'll keep it. All right. Well, I'm going to move it anyway. I just changed it, and I realized that there was some stuff on there that I still want to move it to Tuesday. So. All right. Last bit of stuff that we're going to talk about with transformations, so that next week we can get into eigenvalues and eigenvectors again. We've already talked about eigenvalues and eigenvectors a little bit, so we're going to end the semester with that stuff as well. Cool. All right. We've already talked about these definitions, but just to remember, again, 1-to-1 means. Yeah. So that's a way to tell, right? If the kernel is 0. Oops. The kernel of the transformation is 0, right? The actual definition says that if I have T of V1 equals T of V2, then what had to happen? Yeah, V1 is equal to V2, right? But this is equivalent to checking whether or not the kernel is 0. That's exactly right for transformations. For onto, if W is in W, what is it? Oh yeah, okay, we're going to get to that too. But the definition for onto says if we start with something in the codomain, what's true? Okay, so the exactly one part would be the 1-to-1 part, but for onto is that there is one, right? So there exists something in the domain such that T of V is equal to W. By the way, if you want some shorthand math notation for different things, you may have seen it before anyway. If you use a little backwards E, that's a there exists. If you use a backward element symbol, that's a such that. If you like math shorthand, that's math shorthand. Take abstract algebra next semester, I'll be using a lot of that. So 4 of you are very happy about that, I'm sure. It's fun. I was raised. That stuff's fun. So. We're going to have a good time. Well, at least I'll have a good time. I don't know if everybody else is going to have a good time, but I'm going to have a ball. So, all right. Anyway, in terms of the range, that tells me the range of T is all of the codomain, right? That's our writing it as a range space. Devin already told me what the check, you remember what the check is, so go ahead and tell me what the check is. Pivot every column for the one-to-one, good. So the row reduced echelon form of the matrix of the, we're doing one-to-one now, sorry. You're exactly right for the range. The reduced row echelon form of this matrix for T has a pivot in every column. And for a range, for onto, it's the reduced row echelon form of T as a pivot in every row. Yeah. Bless you. And this is why I wanted to go, it doesn't matter if we use the standard matrix for T or the matrix in terms of different bases for the domain space and the codomain space. These are still true. If you have any matrix that represents the transformation, standard matrix or not, if you have a representation of the transformation as a matrix, these checks are the same. Row reduce the matrix, pivot in every column, one-to-one, pivot in every row, onto. Okay. Doesn't matter if it's a standard matrix or not. All we need is a matrix representation. All right. This one asks us if we can do check if this is one-to-one and onto. We've got transformations from polynomials of degree 1 or less, so constant polynomials and linear polynomials, to the real numbers defined by integration from -1 to 1. Okay. So this one asks, let's check if it's 1-to-1, check if it's onto. That's the idea here, right? All right. So let's do onto. We could find a standard matrix here if we wanted to. We should be able to tell one or the other, not being one of the other. You can just look at the spaces and tell me whether or not it's not 1-to-1 or not onto. We talked a little bit about that last time as well. We're going to review that here in a minute. But what's the dimension of your domain space? 2. What's the dimension of the output space? 1. Right? The real numbers just has one dimension, right? Everything's generated by 1, if you will. Right? Okay. So which is it not? Is it not 1-to-1 or not onto? Yeah, it's not 1-to-1, right? The domain space is too big, right? Think about it this way. If it's 1-to-1, that means that I can map an exact copy of the domain into the codomain. That's what 1-to-1 does. It maps an exact copy. Okay? I can't stick a dimension 2 space into a dimension 1 space. So it can't be 1-to-1. Okay? Could be onto, doesn't have to be, but it definitely cannot be 1-to-1. Right? Too big. A way to check that, of course, is with the kernel idea. We can show that the kernel is not just the 0 vector. Okay? So can you tell me an easy linear polynomial that integrates to 0 over -1-to-1? Certainly 0 does, right? I need something that's not 0. Can you tell me an easy linear polynomial? Yeah, just x, right? If I use x, the integral from -1-to-1 for x is just 0, right? It's odd for 1, but if you think about the picture, I got a triangle here and a triangle here that has the same area. One's above the x-axis, one's below it, right? So t of x is 0, right? And certainly t of 0 is 0, so t is not 1-to-1. Fancy word for 1-to-1 is injective. How about onto? What's that? Injective is inject and then IVE. Yeah. So. All right. What about onto? Do you think you can get every real number out from linear polynomials? So again, we would need t of ax plus b to equal some value r, right? When we're done. Agree with that? All right. So we're gonna have to add some constant to it. But notice that first thing we need to do is notice that t of ax is always equal to what? What was t of x equal to? What can I do with the a? Pull it out. So this is always 0, right? So if I want the t of ax to equal some value r, right? I need just the t of b to be r, don't I? Because the t of ax piece is always 0, right? So if I want t of b to be r, what does b need to be? I need the integral of just the constant function to equal r from -1 to 1. So what does the constant function need to be if I wanted to integrate to r? Oops. If I want the integral to equal r, I want that area to be r, don't I? What's its base? Its base is 2. So what do I need the height to be to get the area to be r? Half of r, don't I? I need to use half of r, and then the integral will equal r. So is this onto? For any real number that I want as an output, can I find a function that makes that integral be r? Yeah. So it is onto. Pardon me, goodness. We could have also done it with a matrix. Since we were going from dimension 2 to dimension 1, we would have had what size matrix? 1 by 2. Plug in your basis for P1. What is a basis for P1? X is one of the vectors. What's the other one? 1, right? 1 comma x will be a basis, right? You plug in 1 into the transformation, you'll get 2 out. Plug in x, you get 0, right? So the standard matrix for this transformation would be 2, 0. Right? That would be the transformation for this, or the basis for the, let's try that again. The matrix for this transformation. Is that going to have a pivot in every row when you row reduce it? Yeah. A fancy name for onto is surjective. So replace the in with sur. I believe that's the French word for on, isn't it? Anyway, doesn't matter. It's surjective. If you're both injective and surjective, then you're bijective. I know, lots and lots of words. Okay. All right. Let's look at the next example. Dimension to dimension. Let's look at the dimensions. What's the dimension of the inputs? What's the dimension of your domain? 2. Dimension of the codomain? Also 2, right? It's R2, right? So can be 1-to-1, can be onto, but doesn't have to be, right? As a matter of fact, since it's 2 to 2, your matrix, If you form a matrix, it'll be a 2 by 2. So if it's 1, it's the other. Right? If you have a square matrix and you get a pivot in every column, you by default get a pivot in every row and vice versa. Right? So it either has to be both or neither. Right? I would do this with doing our standard matrix. So again, if I do T of 1 and T of X, what vectors do you get out when you do T of 1? What vector do you get when you do T of 1? 1, 1, and for X, 0, 1, right? So if I make the matrix here, is that going to get a pivot in every row / column when you row reduce? Yeah. So this is an example of a bijection. Notice when I formed the matrix there, I assumed I had the standard basis for R2. I thought I had those coordinates, right? The coordinates of 1, 1 are 1, 1. I need to type this matrix in and row reduce it to get both answers. But you should be able to tell me one answer for sure. Which is it not? 1 to 1, right? I can do it from both dimension and looking at the matrix, right? Dimension of the input is 6, dimension of the output is 4, right? Can't be 1 to 1. Could be onto. I'd have to row reduce it and check, right? But certainly when I look at the matrix, can I possibly get a pivot in every column? No, not possible, right? So I see some people typing it in for me. There's a couple of reasons that we can say it's not 1 to 1. First one, dimension of R6 is 6, which is certainly bigger than 4, which is the dimension of your output. That's one reason. Another reason is we cannot get a pivot in every column of the reduced row echelon form of A. Is there a pivot in every row? No? Okay. Okay. So if you row reduce it, it appears that we don't get a pivot in every row. You can check by typing in row reducing it. I'm assuming you're all okay with doing that at this point. Typing in a matrix and row reducing it, which is why I didn't bother going through it. So far, so good? Okay. All right, we've already talked about this, but let's summarize it so we have it in the same area. We have a transformation. Dimension of your domain is n. Dimension of your codomain is m. What I'm asking about this is that if I'm asking, can you tell, is it 1 to 1 or is it not 1 to 1 or is it not onto by default? That's what I want to ask with these questions. If your domain space has a smaller dimension than your codomain space, which can't be possible, cannot be onto, right? But it might be 1 to 1. Again, the idea would be that if it were onto, you're taking a smaller dimension space and trying to stretch it over to a bigger dimension space. Right? That's what I would say. Let's think about it the other way. If you were to do this with a matrix, remember if this has dimension n and this has dimension m, you get an m by n matrix, and you'd have more rows than columns, so you can't get a pivot in every row. That's another way to think of it, right? Matrix for T would be m by n. So you'd have more rows than columns. You have more rows than columns, you can't get a pivot in every row, right? How about the other way around? If your domain space is bigger, what can't it be? 1-to-1, right? Could be onto. Again, your matrix would be m by n. In this case, you'd have more columns than rows. And if you have more columns than rows, you can't get a pivot in every column. Right? How about if they're equal to each other? If it's one, then it's the other. It's exactly right. It could be 1-to-1, it could be onto, but if it is one, then it has to be the other, right? So if it's 1-to-1, then it's onto, and vice versa. So if the dimensions are the same, if it's injective, it's automatically bijective. If it's surjective, it's automatically bijective. You use new words that we learned today that you were all very excited about. All right, so let's look at these spaces. Again, just quick checks using dimension. How about T? Yeah, well, they're all T. How about the first one? Could be 1-to-1, but not onto, right? Dimension of R7 is 7. Dimension of R9 is 9. So T is not onto. Could be 1-to-1, but definitely cannot be onto. Okay. Next one, dimension of P8 is 9. Dimension of M23 is 6. So which can't it be? 1-to-1. Finally, the last one, your dimension of P5 is 6, and the dimension of R6 is also 6. So what does that tell you? Both are, yeah, if it's one, it's the other, right? It's the only thing we can say, right? It's either both or neither. Best you can say, right? It's either both 1-to-1 and onto, or it's neither 1-to-1 nor onto. It's the only choice you have. All right. So just briefly, we'll talk about the definition here for your inverse. We can define the inverse transformation Well, remember, inverses just reverse your roles of x and y. Your x and y here are just your inputs and your outputs. So the inverse of something in your range is something in your domain if and only if when I plug in v, I get out w. Notice that as long as the transformation is 1-to-1, you can define an inverse function. It just may not be on the entire codomain. It would be on a piece of the codomain, right? You've done that before, right? In algebra class. When you do the inverse of the squaring function, what do you use? Square root, right? But that square root function is only defined from 0 to infinity, because your x squared only has outputs that go from 0 to infinity, right? So that's all I mean by putting the range of t in here for my inverse, is that if it's 1-to-1, you may not have hit everything in the codomain, right? But I can still define my inverse on that piece. And it's defined just like what you would do in an algebra class. Now, how do you think we're going to find, just as a brief thing, I know we're out of time, but how do you think we're going to find an inverse? Well, remember, the whole point of doing the previous stuff was find the matrix for the transformation. So how do you think we're going to find the inverse transformation? Find the inverse matrix, exactly. That's exactly what we're going to do. So that's what we'll do on Monday. We'll talk about how we find the inverse transformation by creating a matrix for the transformation. See if the matrix is invertible, and then invert that. So that's exactly what we're going to do. So we'll talk about that on Monday. We'll also get started into eigenvalues and eigenvectors again. And like I said, that'll be the last topics that we do for the semester. So we're almost done. It's very exciting. All right. Have a good one, everybody. Have a good weekend. We'll see you on Monday.